you come into the thermal fluids lab, the big piece of equipment in the middle of the room is the wind tunnel. And so we'll start with that because it always steals the attention whether we start with it or not. There is a collimator at this end, which makes the air very linear, and a fog machine, smoke machine. And we can mount different airfoils. Airfoil is the technical term for a wing. We can mount the wings in here, and then we can take the things that are taught in fluid mechanics, such as Bernoulli's equation, which converts velocity and pressure and relates them. You can come in here and you can measure it on a wing, and you can not just measure it, but you can see it and visualize it. So I'm going to go ahead and run the fog across this wing so that you can see some of that. And so here you can visualize it. As the fog trails off, the curvature gets really nice. You can see there's a skinny part at a thick part at the front, and then it gets skinnier over the bump. And you're able to begin to visualize, if we get the angle right, and be able to perceive the delta pressure. There's always high pressure on the bottom of the wing and low pressure on the top of the wing. And if you're inclined to say, who cares? Anyone who's ever flown in an airplane, that's how you get the lift, is that delta pressure. So there's numerous balls. We'll take different sports balls that our students play. We've got a LeTourneau golf team with a branded golf ball, wiffle balls, tennis balls, footballs. There's a rugby ball. We have a rugby team. And we'll instrument them up, and we'll mount them on what's called a sting, which is an apparatus that comes up out of the bottom of the wind tunnel. And then we can measure the drag, the air molecules going quickly across the ball or whatever the equipment is. And we can measure the drag. We can send them out into the field to take the ball and guess how fast they will hit it or throw it or kick it. And then based on the angle of launch, and we have a radar gun, we can measure the velocity that these different balls go at. You can see there's a Nerf dart in there as well. We can calculate how far it would have gone without drag, which is what the classic physics equations give us. The more realistic equations have drag in them, and then they can take their experimental data and the drag measurements that they've got from here, their experimental field measurement data on how far it went, and they can actually check for correlation. Different apparatuses in this room. When we run the wind tunnel faster, you've got to wear ear protection. This wind tunnel will actually do 111 miles per hour, which is a hurricane category 3. This is a hot plate, and so we're able to make the surface hot and put air across it and do boundary layer studies. Comes into play in a heat transfer class. We have a thermal imaging gun, a FLIR camera, so we can visualize the temperatures. One of our apparatuses will take a strain gauge and attach it to a beam. So this strain gauge would be attached to this beam. It's actually bonded with cyanoacrylate, which is the fancy term for superglue. And then we can put a load on it, and based on the geometry, the length of the beam, the width and the thickness, we can predict the deflection that you would get, and then we can measure it. And by measuring the strain, we can actually correlate to the stress in the material. And so you can't see stress, you can't measure stress, but you can measure strain, which is elongation. As we pan around, there's more apparatuses in the room. This is a pendulum spring system, and it's got a load cell in it, and it's a simple harmonic oscillator. So we can take a spring and we can measure the diameter of the coils, the number of coils, and the spacing between them with calipers and rulers, and we can characterize them, and then we can mathematically predict the spring constant, that is the stiffness, the force per unit length. But then if we come in here and we put weights on it with a transducer, a force gauge, and get this stack bouncing, based on the periodicity of that movement, the simple harmonic oscillator, we can actually experimentally measure the spring constant. So we calculate it from physical properties, we measure it from experimentation, and we look for correlation. This is part of that hands-on, right? You see it, you measure it, you do it. Another simple harmonic oscillator that we do experimentation on is this pendulum. And so this pendulum is a inverted sledgehammer, and we strike it with a dead blow hammer. And then based on that oscillation, we can characterize the frequency of the response to an impulse. So you look at it, it's a pendulum and it's a weight. Well, when we go apply it to the oscillation of a wing in the air tunnel or the wind tunnel, you go, oh, I'm really glad I did the simple model first. And so it helps our students to come up to speed on these concepts. There's a load cell calibration system here. So load cells are used for measuring force. We can measure the, we can basically calibrate them and characterize them. There's another set of airfoils that go in the wind tunnel here. And you can see there's a bunch of tubes that come out of some of the airfoils, or wings as they're commonly called. And with those we can measure the pressure of the air on the front edge of the wing. It's also a Sharpie, or actually it's an IZOD impact tester, typically used for smaller specimens. How much energy does it take to break something? We can characterize that.